So even if you are standing there in front of an alien machine, all you need to do as an energy auditor is to understand what different inputs are going in, especially the energy inputs, how this energy is being converted into useful work, how much of this energy is being carried forward by the product that we are producing, and how much energy is going out as a waste. So to identify that, we must know where this energy is going. So is it going in waste air, in hot air? Is it going out as a hot water? Is it going out as mechanical heat? So where is it going actually? How is it being consumed? If we do that, I can assure you that more than 60% of your job is done in terms of the process. When it comes to what is happening inside the process and how to improve the process, optimize the process itself, it happens very rarely that a textile company allows us to comment on their process parameters, to trials with their process parameters. So usually, if we only look around the machine and see the inputs, see the outputs, including non-product outputs and product outputs, then we can pretty much say confidently that we can do an energy audit of that process. So what we'll do today is that we'll discuss about typical production and process flows, input output aspects, performance benchmarks, energy consumptions, and energy performance and efficiency opportunities. This is the textile value chain where the process steps start with production of fibers. Natural fibers are produced using land. So they're, for example, cotton crops, and then we have pesticides, preservatives, water demand, and obviously we need a lot of tractors there, and we need a lot of energy going in terms of diesel there as well. And then man-made fibers, these are purely industrial processes where we procure synthetic materials and then we convert them into fibers. There's a lot of wastewater there, pollution, air emissions, and these textile auxiliaries are not biodegradable as well. And then we have a lot of energy consumption here as well. In yarn production, when we are producing the yarn for further use in fabric making, for example, we have processes like spinning or twisting. I will explain these processes going forward, but at the moment I'm just giving you a summary where we have mainly electrical consumption, and then we have wastes like noise pollution, dust emissions, fiber waste, a little bit of auxiliary and chemicals as well, where maybe we have to apply sizing to it before it goes to the weaving process. Then we come to weaving or knitting, where we are producing the cloth, and these are also usually electricity users rather than thermal energy users, except for few of the processes where we might need to apply sizing or do a de-sizing after weaving. If we have a fabric process afterwards, if we don't have a fabric processing unit afterwards, then we apply the size after this to control shrinkage, and then we send it to the fabric mill, which does the de-sizing first. So we have electricity consumption mainly here, but if we have a fabric processing afterwards, that is textile finishing, there we have pre-treatment, dyeing, printing, and finishing. All of these processes are high energy users, high water users, high wastewater polluters, high chemical users. So usually when we are working on environmental performance improvement, this is the first segment that the international buyers as well as the international community starts focusing on. But now, since they have understood that this process is very much understandable now and people know what to do, they have started focusing on the back end process as well. And if you look at the concepts like cradle to cradle or cradle to grave or value chain analysis, these are the typical process. Or if you know Better Cotton Initiative, for example, they really look at this first process of cotton production and see how this cotton can be produced in a more environmentally friendly way, or what we call a green cotton, for example. The color is obviously not green, but we just tend to put this word green with all the things that we think are sustainable. And then making up, or the garment making process, where we have cutting, assembly, finishing. In finishing area, we might have high water demand if we have denim finishing, for example, and then we have packing. So this is a general textile value chain, but now we will discuss them one by one. So let's start with yarn manufacturing, or what we commonly call as spinning. So this is one material flow chart or material energy flow chart that I developed for one company, that is for a textile yarn company. And you can see that what we did was that we divided them into different quantity centers. So this quantity center concept comes from the concept of material flow cost accounting. So this means that this is a concept which is a little bit new, but it's not very difficult. You remember that we did last time. We developed material flow chart, and we developed an energy flow chart. So this material flow cost accounting simply combines both energy flow and material flow. It's simple. You can see process 1, process 2, process 3, process 4, and so on. And then we show what are the inputs. So for example, in the process 1 or quantity center 1, I will explain to you later why we call it quantity center. We have cotton bales that go in. Then the output here, or the sub product here, is blending, and then we have some wastes in the bottom. Then Q2, QC2, that is quantity center 2, where we do the beating of cotton. And then we have beat cotton available after this process. And then this beat cotton goes to the next process, that is sorting or beating. So beating again and scutcher. This process converts this cotton, beat cotton, into laps of cotton. So pieces of or sheets of cotton. This then goes to the next process, which is called carding, where it starts converting these laps into rope form. So these are long ropes which come out of this carding process, and then they are just piled up in drums, and these are called sliver. Going forward, the sliver enters the drying process, where we have a 2 or 3 or 4 stage drying process, depending on how long we want to have this yarn. So this drying process converts actually what it does is just thins the rope and elongates this sliver. It is still called a sliver because we have not twisted it at the moment, and we have not converted it into into yarn. And we still do this. We further do it in QC7. Sometimes it's called process also called simplex. Then we go to the process called ring, or the real process, which is the spinning process. Here we have spinning, we might have twisting, and in twisting we have different kind of twists. So what we do here is that we take this sliver that came in, and then we start twisting it in the machine. When we twist it and we stretch it, it starts to become yarn, and then this yarn is actually wrapped around the cones, small bobbins, which is kind of a finished yarn that we have. How it is done is that we twist it, and then based on the number of twists, the number of steps of processes vary. So if we have only single twist, we might have only one step of machines. But if we have a process called doubling, where we have double twist, these are the thicker and stronger yarns where we have done doubling, and these are used for example, areas where we need more strength in the yarn. So we have small bobbins coming out of this process that we call ring, and the machine is called ring frame. And normally the size of spinning mill is calculated based on the number of frames they have. So the number of bobbins they can produce it at one time. So some the people say, for example, we ask about the size. A small mill is normally 25,000 frames. Bigger mills are 100,000 frames. So they can produce 25,000 bobbins at the same time. Then these bobbins go to the next process called autocone or the coning process. This is where the bobbins are loaded onto the machines and then they are converted into cones. These cones that are sold in the market, or if you go to weaving mills, you can see these cones lying around there in the stores. So this is how the process is. And all of these processes have electricity consumption, and this process called autocone has very high, and the ring as well. So these two processes have very high consumption of compressed air as well. Now, why the term QC? The ISO standard, I forgot the number of this ISO standard. Maybe you can look up internet in parallel. There is an ISO standard for material flow cost accounting, and this requires us to combine the processes or define the processes into quantity centers. So for example, in case if you see that QC1 on top, either it's very small written, but maybe you can read, QC1 has 3 processes in it: mixing, plucking, and blending. The problem here was that that from mixing, the factory was not doing any measurement of material output. And so what they were measuring was they were measuring the material output after blending. So we did not have material quantity at mixing and material quantity at plucking. All we had input for mixing and output for blending. So we combined them together into one quantity center. So quantity center is a set of processes for which we can define the quantities of inputs, outputs, and wastes. You can see that we did a bit of blending here. For energy consumption, we had meters only combined for QC5, QC6, and QC7. But just to ensure that we are able to divide the processes in detail, because we had material quantities here, we did not actually combine them as one quantity center, because we also had measurements of the wastes here as well. So we did an estimation of this energy, divided this into these quantity centers evenly or based on the experience a little. We can also do spot measurements there. So this is the same process that you did last time. You developed an energy flow chart, and then we did an energy balance, right? So you combine them together and becomes material flow cost accounting or material flow accounting chart. So all these processes are only consuming electricity. So this first process, for example, mixing, plucking, and blending, what we do is that we get cotton in shapes of big bales. So these are very, very big piles of cotton. We open them up and we start to mix them. So this mixing is done on a manual machine usually. And then there are, 20s or dozens of people sitting there, workers sitting there, to do the plucking. So what do they pluck out of it? For example, if there are any cotton seeds in the bales, they pluck them out, or any impurities, any straws in there, for example, any impurities that are coming from the field or from the baling process. And then we blend them together. So here we decide if we need to do blending or do we need to produce pure cotton. So if we have, for example, a blend of 80% cotton and 20% synthetic, this is where we start the blending process. So we add that material here. So with the blending process can also be done afterwards when we're producing yarn, but the different processes for that. And the waste that come out of here is contamination, dust, and if there is any very, very short cotton fibers that come out. From the beating process, that is QC2, we beat the cotton in a way that it opens up. So all the fibers, they open up. You might have seen this process also in the cottage industry as well, where they do the cotton beating to fill in the blankets as well. Then we have further beating. So here we do some more sorting. We remove some further contamination. Once the beating is done, we blow up the cotton using big blowers, and then we do the beating again. So this is where the beating is literally refined, and we have pure cotton labs coming out of here. And then in the carding process, we put them in the machine and we start drying them very slowly, so they start becoming taking the shape of a tube or a rope. We call it, don't call it rope because it's not twisted. It's like a non-woven tube that is coming out, which is called sliver. And here again, it is purely energy. And in all these processes, we also have fluff filters. These filters take air from the machine, exhaust the air, and then there are these jute bags or cotton bags used as filters where we can collect the waste. For example, if there's liquor, there's short fiber naps, or dust or impurities that come out of this process. And then some reusable waste also comes out of here. That is some cotton fiber that comes out from this process. So this sliver then goes to drying process where we draw it further. Because we also have filters here, some short fiber also comes out of here as the material waste. This cannot be reused. And these processes are also only using electricity, where we mechanically pull the sliver to make it longer and thinner. And this is where we have a lot of compressed air being used in this twisting process, or the spinning process. We twist it, and while twisting, we need a lot of stretching of the yarn. We need to maintain tension in the yarn as well, because then we have to put it around a bobbin as well, so that it can then be used in the cones. In the auto coning process, there are a lot of very small pneumatic cylinders which are operated using the compressed air, and usually many of these are leaking, especially their connecting pipes are leaking. So normally they can be fixed only by pressing a little bit, but because with passage of time there's heat in the process generated mechanically, so these actually become brittle with time, and then we have to replace them. So this is how the process is about. So we also did an accounting here. So what you can do is that you can, if you have all the quantities available, you can first do material accounting. So this is similar to what you did for the energy last time. Here we are also combining the wastes as well as output. So for example, these green areas are inputs. So we have material 950 kilograms going in as one batch, and then from out of each quantity center, we have this amount of kilograms coming out. So 950 go in, and 739 came out of quantity center 9 in terms of kilograms. In terms of kilowatt hours, for this batch of 950 kilograms, we had combined input for these three quantity centers at about 141 kilowatt hours, then QC4 264, and subsequently we had others. And then we come out with the total value of kilowatt hours used for the 950 kilograms of input. Number of persons working there. So this is also one important aspect in this ISO standard of material flow cost accounting, that it requires to put in system costs as well, which can be terms as number of persons working in each of the processes for this batch of production. Then we do the quantification of material waste. So we have material waste, we have material reusable waste, and we have dust coming out from different processes, which are again for this input of 950 are quantified in terms of kilograms of output. Then we have the total material non-product outputs, NPOs. We combine them together, and we have different NPOs for each of the processes. We have a total of 211 kilograms of NPO in terms of material. And then what we can do here is that we can see how much percentage of this NPO is against the total input quantity. And then we assign the same percentage to the energy input. So we assign the same percentage here to 141, and we come down to 29.6 kilowatt hours of NPO directly going out as that is producing the waste. And we also assign the same percentage to the persons or the system cost, and then we get this in terms of number of persons. So 49.1 person equivalent input is going into waste, and 405.5 kilowatt hours of energy is going into producing this 211 kilograms of material NPOs. Obviously, there would be other NPOs which we can quantify if we do detailed measurements. For example, if there is a process which has waste heat, we could even estimate the quantity of waste heat going out, and then we could add, for example, that to the energy NPO here, the quantity of waste heat that is going out, and that would add up to the NPO as well. You see, we have total material NPO here, right? 4.5, 11.2, and 19.0 kilograms of material NPO coming out of these three quantity centers combined. So if we put them together, if we add them together, it adds up to, I think it's 35 somewhat kilograms. Then we divide it with the input quantity. Okay, so how much input went into these three quantity centers? So this percentage of waste is then assigned to the percentage of kilowatt hour input, because this was the energy that was used to produce this material NPO. This energy was not used to produce the material or the product output. It was used to produce NPOs. So the same fraction of amount that goes into kilograms of NPOs against the input quantity of kilograms of material can be assigned to the input of kilowatt hour as well. And same percentage or same fraction can then be assigned to the number of persons. So the next step then would be to assign costs to all of these. So what we need to know is how much does 1 kilogram of material cost, how much does 1 kilowatt hour of energy input cost, and how much does one person cost. Then we also need to know if we are selling some waste, and does it produce any revenue for selling, or do we have to give a disposal cost to a vendor. So we need to assign those here as well, and based on that we can calculate all the costs, and subsequently can also calculate the NPO costs of material, of energy, and of system NPOs. So this is a sample cost calculation for you. For example, we had these are values on Pakistan rupees, because this was a Pakistani company. So we have converted all the quantities now into Pakistani rupees, as you can see. So the output quantities then have these values, and then we have energy input values coming here in monetary terms, waste values. The values in negative show that these were sold, so these are revenues. But negative because we have put all the costs as positive, so revenues go as negative. So when we do these, for example, 791 minus 43, we have the NPO cost as 748, then the energy cost, and then the system cost. Here in the right hand side, we can see the total values. So we have total inputs, and then we have total outputs and total NPOs put in together in terms of cost. So earlier we had this in quantity data, and now we have this as cost data. And then we can create a summary, for example. So 79% of material went into the product, 79% of energy went into producing the product, and 79% of system cost went into producing the product output, and 21% went into producing the NPOs. And since we also had some disposal costs, so the total amounts were not 79 and 21, but the total amounts were 72% went into of total cost went into production, and 28% went into NPO production. That is how we can do a summary of this material flow cost accounting as well. What I recommend to you, let me pull up the number of that standards. This is ISO 14053. This is the standard for material flow cost accounting. I think to start with, it's better that you go for 14051, which gives you actually good enough guidance for conducting it. So forget 53 at the moment. This is one of the regression analysis that we did for 35 textile companies in Pakistan for UNIDO. And these were spinning mills. You can see for 100% cotton, we did this was a simple regression because we did not have too much data available. but we got a slope value y is equal to 0.4476x. X is yarn count. If I hope you remember last time when we were discussing the normalization, we discussed this chart there where we had this company A, which is here in the beginning of the line, and the company B was here at nearing the end of the line. We saw that these are both lying on the same line. So this is one of the ways that we can do a specific energy consumption benchmarking. This is put here only for the reminder, but this was the data that we got from an international study. And then we put into this study as well. So you can see that for Pakistan we had 5 gigajoules per ton and ranging up to 33 gigajoules per ton. And for different countries we have different ranges of values. Light gray is for a ring yarn which is combed. This blue color for them is open end yarn, and then we have minimum range dark gray and maximum range dark blue. In this case, you can see India. We also have a big variation. Indonesia, Thailand also very big variation. For some countries, we do not have the minimum or maximum values, but we have values for specific kind of yarn. So these are different benchmarks available, generally ranging lowest values ranging between 3.5 to 3.6, but you can see these are hardly comparable because we don't know which variables they used. An example, energy balance, usually ring is the process which consumes highest energy. Autocone is a process which consumes highest compressed air energy, and also consumes highest energy. So it is 13th, third largest. Second largest are drying and simplex, because there's a lot of mechanical energy going in to draw the yarn to make it longer. The carding process, which converts the cotton laps into cotton sliver, the cotton tubes, is also consuming 14% energy. The back processes, which we call the mixing processes and the blowing processes, are consuming the least energy in this case. The biggest energy utilities in this case are the compressed air system and humidification plant, because these processes, they need humidification. If we don't maintain a certain humidity here, the cotton heats up and also catches fire. We also need humidification plant and ventilation system to draw out the suspended fluff. So what we usually do is we provide positive displacement pressure. So from top, we provide more air, and from the bottom, we do an exhaust. So the air from the top presses the suspended particles downwards towards the exhaust, which is from the bottom, which is from the floor. And then the whole air carrying the fluff goes through the exhaust. Then it goes into the filters, so that all this fluff and dust is collected inside the filters, and the clean air is then exhausted. Different options. So in compressed air system, I mean, we have the demand side pressure optimization, leakage reduction. These are the bigger issues here. So in one of the textile mills where we went there, they were using 2 compressors of 90 kilowatt and for 2 compressors of 45 kilowatt. And the pressure they were using was 9 bars in the generation side. When we did a detailed analysis in the demand side, we did not find any machine which needed more than 5 bar of pressure. They had only one small testing equipment in the lab which needed 7 bar pressure and not more than that. So we requested them to, number one, eliminate the leakages, and number two, gradually start reducing the pressure. So they came down from, at the first stage, they came down from 9 bar to 7 bar, and one of their compressors went into shutdown. And after few weeks, they were able to shut down one 9 kilowatt compressor, a 90 kilowatt compressor, and one 45 kilowatt compressor. What we did was to optimize the pressure based on the demand side pressure. That's it. Then the ventilation and humidification plant, as I told you, that there are supply fans and there are return fans, and we have to maintain 3 to 5% positive pressure. That means that the quantity of air being supplied by the supply fans is 3 to 5% more than the quantity exhausted by the exhaust air, because the particles of fluff, these are lighter than air, so they suspend in the air. So we provide more air from the top and less air is exhausted, so it pushes the air down, pushes the fluff downwards. So if you enter a spinning mill or a weaving mill, and if you see particles suspended in the air, fluff particles, that means that their positive pressure is not being created, they are creating negative pressure. So the options here are optimization of supply and return fans. So we can, for example, go for lightweight fans. If you have metal fans, we can go for fiber reinforced plastics or plastic fans. We can also see if they are supplying too much supply air, more than 5%, or if they are exhausting too much air, we can slow down the exhaust fans. That is how we can also do the optimization. And if they are doing humidification, for example, they have fogging system there, what we can do is we can do a humidity sensor, we can install humidity sensors in the in the spinning section, and then we can feedback it to the humidification plant, and we can control the pumps and the fans there to do the optimization. So that is how we can optimize the ventilation and humidification plant. Inside the machinery, the cotton from the first process till the carding process is transported using blowers. So its cotton is in the pipes, then there are blowers which are blowing the cotton, and it is transported with the pressure, the push pressure of fans or blowers, and the cotton goes from one process to the other process. We have seen often that these blowers are neglected and these are not automated as well, based on the amount of cotton that is being delivered. So these can be automated. Then avoiding fluff accommodation. So this cotton fluff, very, very tiny fluff, accumulates inside the machines. Then it increases friction, especially in the ring frames and auto cones. When there is too much fluff inside, it increases friction so much that the yarn breaks. And yarn breakage is very, very dangerous for the spinning mills actually. So they try to control the yarn breakage. And also automating the machine speed according to yarn tension. So in the ring machines, what we're doing is that we are taking the yarn and then we are winding it up on the bobbin. If the tension is too high, the bobbin will be very, very tight, and when we load it to the autocone process, it won't function properly. If the tension is too low, the bobbin will be very loose, and when it goes to the next process, it might create knots there. So we have to maintain a certain tension in the fiber when it comes from the machine and going onto the bobbin rings. So to maintain that tension, we also have to maintain the machine speed. So if we can apply variable frequency drives there, measure the tension, and then vary the machine speed accordingly, we will have less yarn breakage, we will have less quality issues, and we will also have optimized energy consumption. So these are some of the options that are there. In terms of energy efficiency, it is a simpler facility. A spinning mill is a simpler facility where we have only electrical energy generally, and some and can compress air, and we just have to optimize it with the known technologies that we already have. So process itself is something that I usually do not touch on, because this process is so complicated that if you do not have in-depth knowledge of setting the machine parameters, you can end up messing the product. So it's better that we do not touch the process unless we have a real process expert with us who knows how to set machine parameters. There are obviously options of optimizing machine parameters as well. One option that I've shown you here, for example, is optimizing machine speed and optimizing the exhaust and cleaning processes. These are usually the process. The biggest savings can be achieved from the compressed air system and the humidification and ventilation plant. Weaving is, common methods are, we used to have these power looms. We still have these power looms in the cottage industry in Pakistan, which are totally electricity driven. Then the water jet looms are used for synthetic fiber. Then there are air jet looms and there are rapier looms. Air jet looms and rapier looms are most common looms now used in the cotton or blended fiber fabric production. So air jet looms are usually suitable for plain and textured fabrics, fine and high density fabric, as well as high speed bulk production. Rapier looms, we can have multicolor weft as well here. Then we can use dyed yarn here as well to produce fabric. I mean, dyed yarn can also be used in air jet looms, by the way, but it is more recommended to use rapier looms. Then we can have double layered velvet fabrics, terry fabrics, decorated fabrics. These are slower than air jet looms, but the energy consumption is also moderate. A usual energy balance of a weaving mill is that biggest energy is going into air compressors. In this factory, 62% of electrical energy was going into air compressors, 70%, 17% was going into weaving process, 11% was going into air conditioning and ventilation system. So the air conditioning system and humidification system here is also very similar to spinning, where we have to do humidification, we have to do fluff removal, and we have to do a certain number of air changes inside. And inside the air conditioning or ventilation plants, fans are the bigger consumers, and then we have pumps, which are also smaller consumers. Inside the compressed air systems, apart from compressors, we have cooling towers and we have air dryers, which also consume energy, and then we have some lighting. This is a usual energy balance of a weaving mill. And this mill was also doing some sizing as well, so some of the energy is going into sizing as well. So the energy consumption ranges, these are energy consumption ranges. For example, in Germany, they range from 11 gigajoule to 65 gigajoule per ton. In India, we have different ranges available, ranging from 18, 19 to 32, 33. Indonesia is lower, depending on what kind of fabric they're producing, what kind of yarn they have, is it mixed, is it synthetic. So this study did not provide us with with these kind of variables. So these are hardly comparable. As you can see, these are not normalized. Only simple normalization is done, which can hardly be used. Efficiency options. So again, controlling air leakage is very important. Usually when we shut down all the looms, we hear a lot of hissing sounds. There are many tiny pipes, tiny link pipes, and inside the air jet looms, inside the rapier looms as well, where these leakages can account for up to 15 to 20% of total air demand. Common areas where the leakages take place are relay valves, tuck-in cylinders, suction mouth, pre-winder, and internal PVC link pipes. These are the areas where you have to look for leakages. But if you shut down the whole process, start the compressor, you will hear a lot of hissing sounds, which some of them can be repaired right away. Then optimizing the compressor pressure according to the yarn count. So mostly higher pressure is provided to cover for pressure losses due to leakages. And also, I mean, if we have high density fabric, we need more compressed air pressure. We have low density fabric, or the yarn count is lower, we might need lower compressed air pressure. This is something that we need to optimize. I always look into the design data of the machine and see what is the maximum pressure required. And usually factories are providing 7 bar or 6 bar pressure, and these machines usually run at 4.5 bar pressure. They have internal pressure reducing valves that are put to 4.5 pressure, and that is how they run. Then air conditioning and ventilation parameters can be automated similarly to what we do in spinning. In this case, we also have temperature control. So we have chillers usually, which are cooling down. And in some older companies or smaller companies, they do not have temperature feedback loop to the chillers. If you provide the feedback loop here, the chillers can also be optimized. And then similar way, we can optimize the air balance in the weaving as well, like we discussed for the spinning. And then production planning. So improving machine uptime. how can we improve the machine uptime, how can we reduce the yarn breakage, for example, reducing fluff accumulation in the machines. These are some of the points where which we can look up in the weaving section as well. So pretty similar to spinning. The whole process is electricity dependent, except for the sizing process where we need some steam, some hot water, and some of the chemicals.